In this video, we want to look at the compilation of solution of past questions, Imo State University, Chem 212, that's the organic chemistry, year of 2018-2019. You may want to get your writing materials so you can jot a lot of things down. The first question says, define the term geometric isomerism and give two properties of geometric isomers. Now, the answer to that is that geometric isomerism is a type of isomerism where two isomers have restricted rotation somewhere in the molecule. It is as a result of the presence of pi bond. So that is it. Now, for the properties of geometric isomers is that they are stereoisomers. Number one is that they are stereoisomers because they have the same structural formula, but different spatial arrangement of atoms. The second one is that they have different physical and chemical properties and can be separated by conventional techniques like fractional distillation, gas chromatography, and so on. The third one is that in the trans form, the molecule, that's the trans form, the molecule are closely packed. Because of that, the trans isomer is more stable and has higher melting points. Number 1BI says draw the structures of D plus glyceraldehyde, D plus glucose, L plus alanine, L minus serine, and lactic acid. Let's begin with the first one. The first one is D plus glyceraldehyde. So, although aldehyde, hearing aldehyde, you know the functional group. So, we just draw it. Then here we have OH, here we have H, and here we have CH2OH. So, this is the formula. The second one, D plus glucose. We have OH and then H. We have OH. Or let's put it this way to show that O is bonded to this. O is actually bonded to this. Then here we have H. Then here we have OH. Then here we have H. Here we have OH. And here we have H. And then we have 1, 2, 3. So it's complete. Then here we have CH2OH. So this is the structure for D plus glucose. That is this. So the third one is L plus alanine. So L plus alanine, let's draw here. L plus alanine, we just have this CO2, H, then here is H, then here we have an amine group. The reason we have it lateral inversion is to show that the bond is attached to the nitrogen, not to the hydrogen. Okay, then here we have CH2OH. So this is the structure of L plus alanine. Then the other one is L negative serine. Let's draw here. We have this CO2H. Then here we have H. Then here we have an amine group. And then we have CH2OH. I beg your pardon, here is L negative serine, but here is supposed to be a methyl group. Sorry. So correct that, a methyl group, Me. So cancel out this, a methyl group. Just remember, that's the difference between the positive and the negative. So methyl group is here on the positive alanine, negative serine. So the other one is positive lactic acid. Positive lactic acid. So since when we hear lactic acid, we already know the functional group is this. So we have this C, we have H, we have a methyl, then we have OH. So that is it. The next question says give two properties of diastereomers. The answer to that is that the first property is that they have different melting points. The second property is that they have different solubilities. The number 2 question says define the following terms. I, mesomerism, diastereomers. Let's start with the first one, mesomerism. Mesomerism is the migration or delocalization of the pi electrons or lone pair electron from one atom to another, which results in the... So let me give an illustration for that. If we have a phenylamine and we have here, and here, remember there's a lone pair here for this. So this lone pair will move to this bond and the pi electron will move to the carbon atom here. And so as a result of that, we are going to get this moving here will create a double bond. Creating a double bond there. This one receiving the pi bond becomes negatively charged, and then the charge electron will also move to this point, and the bond here, electron comes to the carbon atom that is here, and because this person has lost an electron, it becomes positively charged, so it moves to the next one. We'll still have positively charged, and the double bond will come here. This coming here, the double bond will also come here, and the charge electron will also move again to this point, and also the double bond will shift, the electron coming to this carbon atom here. So the next thing we're going to have is double bond is here, this has shifted to this point, here is negatively charged because it has received an electron, it is now negatively charged, double bond is here. So this will also come to this point again, and when it comes to this point again, we're going to have this again will come back to this point. What it will now result is where it started originally. Where it started originally. So you will still have back your lone pair electron. And remember, it goes back and forth, continues to go on and on. The next one is to define diastereomers. They are stereoisomers that are not mirror images of one another, and they are not superimposable on one another. And stereoisomers with two or more stereocenters can be diastereomers. An example of that is if we have CH3 and then we have COH, we have H, we have C, we have H, we have bromine, we have CH3. Then there is mirror. Then on this other side, we still have methyl, C, H, OH, then we have C, bromine, then H, then we have CH3. So you look at two of them, you can see they are not mirror. This different compound, we call it compound A, we call this compound B. So you notice that they are not mirror image of each other, and they are non-superimposable. If we have another CH3, OH, H, C, Br, H, CH3, and then we have a mirror, and we have CH3, we have H, we have OH, we have C, we have H, we have bromine, then we have CH3. If we call this C, compound C, call this compound D, you notice that compound A and compound C, they are neither superimposable nor are they mirror images. So because of that, A and C are called diastereomers. The next one we are defining is position isomerism. It is shown by the compounds having the carbon skeleton but differ in the position of the substituent group. What we mean by that is that if we have CH3, CH2, 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 1, 2, 3, 4, and then we have a bromine, then another compound, CH3, CH, and let's say Br, and CH2, C, 1, 2, 3, CH3. You can see that the substituent group is bromine. In this place, it has the first position attached to the first carbon atom. And here, it is attached to the second carbon atom. Whether you are counting from here or from here, is second atom. So here, the name is 1-bromobutane. 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 That's here. But for here now, it is 2-bromobutane. So just positional isomerism. 2-bromobutane. The next thing we're defining is functional group isomerism. This is shown by compounds that have different functional groups. That is, they belong to different homologous series. An example of that is if we have ethanol belonging to alcohol group, then we have let's use methoxymethane. So methoxymethane, methoxymethane. So you can see both of them have two different functional groups, two different homologous series. But how many carbon atoms? 1, 2. How many carbon atoms? 1, 2. So this one is alcohol group, this one is an alkoxy group. The next question. So this question says, using the ROS system of nomenclature, arrange the following in the order of their naming priority. Okay, this is the first one. So for us to answer the first one, if we are to arrange it, iodine comes first. After that, bromine. After that, sulfur. After that, OH. After that, CH3. Now, their atomic number is what play a major role in this. So, the next one, we begin with CH2I. That's this one, comes. The next one is CH2Cl. That's this. The next one should be CH2O. That's this one. Then the next one should be CH2NH2. Then we have CH2D. So the next question says, give 4 methods by which racemic mixtures can be resolute. The first method is by mechanical separation. Mechanical separation. The second one is biological separation. Then the third one is by means of salt formation. By means of salt formation. Then the other one is selective adsorption. Then how many? One, two, three, four. Okay, you can. Another one is channel complex formation. To make it five, but the question says four, so any four. So this question says, give any five parameters of measuring chemical stability. Now, the first one is heat of formation. The second one is heat of combustion. Another one is dipole moment. Another one is absorption spectra. Then the other one is valence bond angle. 3b says, using reaction scheme, show the reaction of cyclopentane with chlorine. So if this is cyclopentane and you react it with chlorine, this must happen in the presence of light because chlorine is sensitive to light. So either light or heat. So two of them. Then it will give you chlorine comes here to stay. So this is chlorocyclopentane. Chlorocyclopentane. So this is cyclopentane. The next question says, draw the structures of the following. 1-ethyl, 4-methyl cyclopentane. The next one is 1-bromo, 2,4-dimethyl cyclohexane. Now the key here is to first of all draw the parent group. This is the parent group before we now start adding the attachment, the substituent. So we need to first of all draw the cyclopentane. So cyclopentane. So cyclopentane, and that's a 1-ethyl. So 1-ethyl. So first of all, draw the junction here. So this carbon atom with 2 hydrogen, then 1-ethyl, 4-methyl, 1, 2, 3, 4. At the 4, we draw methyl, then cyclopentane. So that's it. Then the second one is 1-bromo, 2,4-dimethyl cyclo. So we'll first of all draw the cyclohexane, which is this. Then 1-bromo. Anywhere we like, we can start the bromo, and that place becomes our 1. But once that place becomes our 1, 2, 4 dimethyl. So it means at 2 and 3, 4 and 4, we have 2 methyl. So here we have methyl. Here we also have methyl. So 2,4-dimethyl cyclohexane. The next question says, draw the chair and boot conformation of cyclohexane. Okay, if you forget it, remember the Facebook Messenger logo. That's how to draw it. So, okay, sorry. Let's draw it, make it. Okay, I think this is better. So here we have hydrogen, hydrogen. Here we have hydrogen, hydrogen. Here we have hydrogen, hydrogen. Here we have hydrogen. Here we have hydrogen. Here we have hydrogen, hydrogen. Then here too. So this is the chair. Looks like chair conformation. Then for the boot, still sorry. This is better. This is the boot conformation. The chair is more stable than the boot. So this is the boot conformation. The next question says, name the following compounds indicating their geometric, that is the trans or cis where possible. So the naming of geometric means call it trans or cis whether when you see it. Now when it is trans is when they are in opposite, one is up, one is down. But when they are cis is when they are on the same plane. Now you can see here now this is on the up plane, but this one is on the down plane. So on this one we call it trans. So if we are naming, if we start from here, we call it trans 1 2 3, trans 1 3 dimethyl cyclo 1 2 3 4 5 6 cyclohexane. So the name becomes trans 1 3 dimethyl, that's 2 methyl, dimethyl, then cyclohexane. Okay, for the second one, you can see both of them are on the same plane. So this is cis. So we call it cis. If we start from here, 1, 2, so we can say go this way, cis 1, 2. So cis 1, 2. We use hyphen to join letters and numbers, but we use comma to separate number and number. So 1, 2, I beg your pardon, cis 1, 2 dimethyl. Dimethyl, that's a hexane, because it's 1 2 3 4. So cyclohexane, dimethyl cyclohexane. Then this other one is you can see this is trans 1 2 dimethyl. So you say 1 and 2. Carbon atom here, 1 and 2. 1 2 trans 1 2 diethyl. So this is ethyl, this is ethyl. Diethyl. This is 1 2 3 4. 1 2 3. Anyhow, you can fold carbon atom. But 2 in because of the double bond. Then the last one is at the second carbon atom there is methyl. There's also so is cis 2 3 dimethyl but 2n, but 2n. So for us to name these ones, we begin with counting the bridges that didn't touch any junction. These are 2 bridges here, they didn't touch any junction, so we say 2. So we also have 1 here that didn't touch any junction. We have another 1 here that didn't touch any junction. We also have another 1 here that didn't touch any junction. So 1 1 1. So 1 1 1, and that's all. So we now count how many carbon atoms? 1 2 3 4 5 6 7 8 9. So 9 is nonane. Then how many segments do we have? 1 2 3. So tricyclo. So tricyclo 2 1 1 1 nonene. On this one, we count the bridges that didn't touch any. So we count 1, 2, 2, 1, 2, 2, 1, 2, another 2. So how many carbon atoms? 2, 4, 6, 7, 8, octane. So how many segments? 1, 2. So bicyclo, bicyclo, bicyclo 222 octane. On this one, you can see here we have 2 that did not touch anyone. Also here we have 2 that didn't touch any. 2. That's all. Then we count how many carbon atoms. 1, 2, 3, 4, 5, 6. Sorry, let's count again. 1, 2, 3, 4, 5, 6. And 6 is hexane. Hexane. Then how many fragments? 1, 2, 2. So by cyclo. So we have bicyclo 2, 2 hexane.